Hello again, Physics 30s. In today's lesson, we are going to continue to look at more specific examples of nuclear reactions, with this time around focusing on radioactive decay. Learning outcomes are to describe the nature and properties, including the biological effects of alpha, beta, and gamma radiation, and to write nuclear equations using isotope notation for alpha, beta negative, beta positive decays, including the appropriate neutrino and antineutrino. Okay, so in terms of what exactly is radioactive decay, it occurs when unstable elements decay spontaneously, releasing alpha or beta particles or a gamma ray. Now, you might be wondering, why are particular elements why are they unstable? Why are they more likely to decay? Well, the elements that are more likely to decay are like our larger ones on the periodic table. And just think about like the nuclei in those larger elements. The nuclei in those elements would have a lot of protons. The more protons you have, the higher that repulsive force would be. So you'd have those elements like really trying to repel and tear the atom apart. So some of those elements over time, and it depends on like the amount of time per element, will start to break apart into something smaller, and that's what we call radioactive decay. The way they do it is they break apart by emitting alpha particles, beta particles, or gamma rays, and we're going to focus all on that in today's lesson. So let's start by looking at alpha particles. Alpha particles are the nuclei of helium atoms. So it's just helium with the outer electrons that have been stripped away. So since helium would have 2 electrons normally, you take those 2 electrons away, and an alpha particle would have a net charge of 2+. Alpha particle in this nuclear notation can be represented by 4,2He, or you could write down 4,2 alpha if you wanted to. Alpha particles only have a range of a few centimeters in air. The reason being is because they're relatively large particles. I mean, it wouldn't take very much for like one of these particles to like strike another like molecule of gas in the air before its motion gets interrupted. So they can't move very, very far. In fact, if you have like just a regular old sheet of aluminum foil, that is enough to actually stop an alpha particle from moving. The density of the aluminum foil can prevent the alpha particle from going through. Beta particles are electrons, specifically high-speed electrons that are ejected from a nucleus. There's a few ways we can represent this in the nuclear notation: 0, -1 E, or we could have 0, -1 beta. Either of those represents an electron. Because an electron is a lot smaller than an alpha particle, even than a single proton, they can move further in air, and they can actually pass through a few centimeters of an aluminum foil just due to their smaller size. And I made a note here, both alpha and beta particles, when they're ejected during radioactive decay, they're typically ejected at very, very high speeds. We've already seen this back in the electric forces and fields unit, and we were talking about these particles a lot. They always had speeds like somewhere around like 10 to the 4, 10 to the 5, 10 to the 6 meters per second. A gamma ray is a photon with a very short wavelength or a high frequency. And a gamma ray has no charge and it has no mass to it. It's just a carrier of energy. So if we want to represent that in the nuclear notation, well, we'd have 0 for the nucleon number because it's not made up of any protons or neutrons, and a gamma ray or a photon has no charge to it. So the bottom number would also be 0. Because a gamma ray does not have any mass to it, it can actually go pretty far in air before getting stopped. So usually a range of somewhere around 2 kilometers, in which case I suppose it'd be like absorbed by particles in the air at that point. Or they can pass through 30 centimeters of lead. Okay, so Alpha particles and beta particles most likely have no chance of getting through lead, but a gamma ray can pass through 30 centimeters of it, which is still quite a bit. That's like a third of a meter stick. One way to determine, so let's say you dug up a sample and you knew it was radioactive and you're trying to figure out, is this sample emitting alpha particles, beta particles, or gamma rays? Is you could take the radioactive sample and you could direct these particles through a magnetic field. Based on the direction these particles would go in the magnetic field, this would allow us to determine what kind of particle is being emitted. Okay, so we need to review a little bit about magnetic forces and fields to talk about this. So first things first, if you have a charged particle enter an external magnetic field, it will be subjected to a magnetic deflecting force. And the equation we used to calculate that was the magnetic deflecting force, Fm, was equal to Q, V, B, times sine theta. Now, a gamma ray would just go straight through the magnetic field. The reason it goes straight through the magnetic field is because a gamma ray has no charge. If it has no charge to it, there's no magnetic deflecting force, therefore the magnetic field doesn't influence it. So if my radiation just went straight through undeflected, I would know it's a gamma ray that's being emitted. Now, in terms of the other particles, well, we would need to use an appropriate hand rule to figure out how to do this. Specifically, it's going to be the third hand rule. Okay, so I'll kind of show the work for like one of the particles, and then I'll just briefly talk about the other one. So let's say third hand rule. Now, if we're talking about an alpha particle is a positively charged particle. So positively charged particle means use your right hand. Now, to use a third hand rule, we need to know a few things. So first of all, we need to know what is the initial direction the particle is moving. So that's the velocity of the particle. And we represent that with our thumb. Okay, so if you look right here, my radiation is being directed towards the right before it deflects. So V be directed towards the right side of the page. You also need to know what direction the magnetic field is, so that's B. And that's the direction your fingers are going to point. The X means, again, follow like what an arrow is doing, so you'd see the fletching of the arrow, so that would be the arrow is going into the page. So into the page. And the final thing would be the magnetic deflecting force, which will lead to the circular motion. So that's going to be your open palm. All right, so the way I would do this is take your thumb, make sure it's perpendicular to your fingers, and I would point my thumb towards the right side of the page. I'd then rotate my hands, my fingers point into the page, and when I do that, my open palm should be facing in a direction that is directed towards the top of the page. Therefore, if I sent this radiation through this field and I noticed the particles were starting to like deflect towards the top of the page, it must be an alpha particle. Now, in terms of the beta particle, we could just use a third hand rule, except you just change things up for your left hand, because it'd be left hand for a negatively charged particle. So again, you take your thumb and fingers, make sure they're perpendicular. With your left hand, thumb points towards the right, fingers go into the page, and this time around, your open palm will be facing towards the bottom of the page. So if the radiation we're looking at gets deflected towards the bottom of the page, then we can conclude it is indeed a beta particle or an electron. I should note you could also do this with parallel plates. If you have like a positive plate and a negative plate, then the alpha particles would get attracted to the negative plate. The beta particles would get attracted to the positive plate. and the gamma radiation would just go straight through. The only difference is that if we were looking at a magnetic field, the motion here would be circular, and the motion of the particles in an electric field would be parabolic. But either would be an appropriate way to try to figure out what kind of radiation we're looking at. In terms of these elements undergoing radioactive decay, oftentimes once they undergo radioactive decay, and they will do that by emitting either an alpha particle, a beta particle, or a gamma ray, whatever isotope is produced as a result, your daughter isotope, usually that daughter isotope is radioactive as well, which means it is also going to decay. This might happen multiple times. So then the daughter isotope would undergo radioactive decay, and it would produce another isotope, and that one would also be unstable, and it would undergo radioactive decay. So the series of all these steps required to eventually get to a stable isotope is what we refer to as a nuclear decay series. Okay, so here's an example of one. So in this illustration, I think we're starting off with uranium-238. Okay, so uranium-238 got lots of protons in the nucleus, not tremendously stable. It'll eventually undergo alpha decay to give you, I think that's thorium-234. Thorium-234 would then undergo two beta decays to give you uranium, this time around uranium-234. Then the uranium-234 undergoes alpha decay to give you thorium-230. Undergoes alpha decay again, undergoes alpha decay again. And then once you get here, it's probability, random probability in terms of like what's the next decay it could follow. But usually most of our elements eventually get down to one of these three elements here. Mercury, I think TL is thallium, or lead. Lead is the one that comes to mind in terms of like being an element that is stable. And I think it's stable just because it has like an optimal amount of binding energy per nucleon, where a lot of the other elements do not. Okay, so that's a nuclear decay series. Just showing all the steps to get from my first parent isotope to a stable isotope at the end. Now, we need to look at these decay processes in more detail. So we're going to look at alpha decay, we're going to look at beta decay, and we're going to look at gamma decay. We're going to look at it beyond just simply identifying which particle is emitting in the decay series. And we're going to do this by looking at specific conservation laws that need to be met in all these different processes. Specifically, we're going to use a conservation law to help determine what is the kinetic energy of an emitted particle by these radioactive substances. So the emitted particle would be an alpha particle, or it would be a beta particle, an electron, or it could be a gamma ray. So let's start off with alpha decay. In alpha decay, we note that there is a mass defect that exists between the mass of the parent nucleus and the sum of the daughter nucleus and the alpha particle. Okay, let's write this in a very, very generic form. So in this equation, this would be my parent isotope, okay? So your parent isotope has A nucleons, it has Z charge or protons, and it's element X. Now, if this undergoes alpha decay, in alpha decay, you emit an alpha particle. Okay, the 42He, that is an alpha particle. If we use conservation of nucleons, that tells us that for my daughter isotope, which is this one, the top line must have 4 less nucleons, and the bottom line must have 4 less protons. Okay, now let's say that I figured out the sum of the mass of the reactants, the sigma MR, and I figured out the sum of the mass of the products, so sigma MP. And then I calculate the mass defects. The mass defect would be delta M is equal to sigma MP minus sigma MR. And we do indeed get a mass defect when this happens. So the mass of the daughter nucleus and the alpha particle is a little bit less than the parent isotope. Okay, so we do have a mass defect. Now, in terms of what do you think the mass defect is going to correspond to? Well, according to Einstein's mass energy equivalence theory, we could calculate delta E. So delta E would be take the mass defect and multiply by c squared. So where's this energy going to show up? Well, this energy, so the daughter isotope is usually like a large element, and because it's a large element with a large mass, it doesn't really move that much after it decays. What's going to move very fast is going to be the subatomic particle, which is the alpha particle. So the energy from the mass defect actually is given to kinetic energy of my alpha particle. And that's what I've stated here. I've stated that, let's get rid of all this junk on the screen. Okay, according to the law of conservation of mass energy, when you calculate the mass defect and determine the energy equivalence, that should be equal to the kinetic energy of the alpha particle. And it is. They confirmed this in the 1920s, so everybody's happy. Okay, conservation of mass energy is validated. Conservation of nucleons works, and conservation of charge is also upheld. Okay, so your mass defect is going to correspond exactly to the kinetic energy given to the alpha particle. So we're assuming all of that energy is given to the alpha particle because it has a smaller mass and they can move at a much higher speed. Okay, so no problem so far. Beta decay involves the production of beta particles. A beta particle is just going to be an electron. Okay, so beta particles are produced when a neutron in the nucleus is converted into a proton. So if we break beta decay down, so in beta decay, we of course emit a beta particle. Okay, so that's my electron. But also in beta decay, something weird happens. Within the nucleus, the parent nucleus to the daughter one, there is a conversion from a neutron into a proton. This has to happen in order to for conservation of nucleons and charge to work. It just seems odd. Like, why is there a conversion from a neutron to a proton? Well, I'm not going to address that right now. In order to properly address it, we need to talk about another fundamental force called the weak nuclear force that is essentially responsible for this. We're going to leave that for a later lesson. Okay, but in beta decay, we do have a conversion from a neutron to a proton, and in the process, we emit an alpha particle. Okay, so let's say that I figure out the sum of the mass of the products, so sigma MP, reactants, sum of the mass of the reactants, and I figure the sum of the mass of the products, and I calculate the mass defect again. So the mass defect would be delta M is equal to, we'd have sum of the mass of the products minus sum of the mass of the reactants. Okay, we'll calculate a mass defect. Let's convert this into energy. So say, yes, we have a mass defect, convert into energy. So E is equal to delta MC squared. And then what is this delta E going to correspond to? Well, physicists predicted this should be the kinetic energy of my beta particle. Okay, so it should be given completely to the electron. I could write this in a more general format, by the way. Instead of writing down one neutron to a proton, we could start off with, again, like element A, ZX. So that's my parent isotope. And then in beta decay, you emit that electron. So 0, -1, we'll say beta. And you would have your nucleon number wouldn't change. You'd still have A. The Z would actually be Z plus 1. Because again, it goes Z plus 1 plus a -1 would just give you Z, and that would give me element Y. Okay, so this one would be, what color do I want to use here? Okay, so this would be your parent. This is the electron. And this is the daughter. Okay, so again, we figure out the mass defect between the products and reactants. We get a mass defect, convert it to energy, and our prediction is that should be the kinetic energy given to the beta particle. The beta particle is the small subatomic particle. The daughter isotope would be much larger, so the daughter isotope would not be getting that energy. So that's the prediction. So we think that this is going to give all the kinetic energy to the beta particle. Now, the problem is the kinetic energy of the beta particle is always less than the amount predicted using conservation of mass energy. Okay, here's what I mean by this. So let's say we used conservation of mass energy and we made a prediction that the beta particle should be getting 20 joules of kinetic energy. It's no way this number is this big. Okay, I'm just making up a fake number. Okay, so conservation of mass energy tells me the beta particle should have that amount of kinetic energy. However, when we actually determine this, the beta particle only has 19 joules. So the question becomes, well, we're missing 1 joule. So where did that 1 joule of energy go? If the kinetic energy of the beta particle is less than what I expected, where is that 1 joule of energy being given to? Well, the problem with our equation for beta decay is there's actually another particle in the nuclear reaction. So there actually is a second particle that's acting as an energy carrier. So what do I mean by this? So let's erase all this ink here. Is we're missing another term. There should be like another plus question mark for another term. So your electron would get the 19 joules, and then your second mysterious particle would get the remaining 1 joule. Okay, and then when you put those two together, they give you the 20 joules that conservation of mass energy would work. So the only way we can explain this is with the inclusion of a second mysterious particle. This mysterious particle is called a neutrino. It's kind of like an italicized V we use to represent a neutrino. Okay, I should point out neutrinos are really, 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 really hard to detect. Why are they hard to detect? Well, they're pretty much massless. Okay, I say massless here. They do have a really small mass, but it's like smaller than that of an electron, and it has no charge. It's really hard to detect particles that have no charge because you can't influence them with electric or magnetic fields. So that's a bit of an issue, okay? However, if we include the neutrino in our beta decay equation, then its existence is supported by conservation of mass energy, conservation of momentum, conservation of angular momentum. So the existence of it is supported. I believe physicists have actually like in some way proven the existence of the neutrino. It's just really tough to do. I think it took them like a lot of years to like figure out like how to prove this thing does exist. Okay, so the beta decay is a little bit tougher because we're missing this particle. Okay, so we're gonna have to expand this a little bit. It turns out there's actually 2 different types of beta decay. There's beta negative decay and beta positive decay, or beta minus or beta plus. Okay, so beta minus decay or beta negative decay. This involves the transformation of a neutron into a proton, and an electron. Okay, we already know that. We talked about that before. We said that on this slide here, there was conversion from a neutron into a proton, neutron to proton, and we get an electron. However, we also get a second mysterious particle called an antineutrino. Okay, now here's where things get really, really weird. Because you're like, okay, wait a second. A neutrino is just this massless, chargeless particle. What's an antineutrino? Well, I have to explain what antimatter is first. Okay, so let's take a particle like a proton. Okay, so a proton has a mass that is, I think, 6.65 times 10 to the negative 27 kilograms. And it has a charge Q of positive 1.60 times 10 to the negative 19 coulombs. An antiproton, which is the antimatter equivalent, so an antiproton would have the same mass, but it would have an opposite charge. So your Q here would be negative 1.60 times 10 to the negative 19 coulombs. Okay, so the difference between matter and antimatter, if we're looking at the same type of particle, same mass, opposite charge. Okay, great. That kind of makes sense. Well, how about for a neutrino and an antineutrino? Okay, so a neutrino, what's its mass? 0. What's its charge? 0. How about an antineutrino? What's its mass? 0. What's the opposite of 0 in charge? 0. Well, wait a second. How can you tell the difference between a neutrino and an antineutrino if they have the same mass and they have the same charge? Well, it turns out there's another property about matter and antimatter. If you take matter and antimatter and you interact them, they will actually annihilate into pure energy. Okay. Specifically, it's going to be energy in the form of like a photon, usually like a gamma ray. So we can't really use the opposite charge to describe a neutrino and antineutrino. All we know is if you take a neutrino and an antineutrino and you combine them together, they will just annihilate into pure energy and give you like a photon or some photons. Okay, so that's what an antineutrino is. It's just the antimatter equivalent of a neutrino, which means if it interacted with a neutrino, it would annihilate to give you pure energy. Okay, let's look at the equation in a bit more detail now. So we're going to include all the particles. So we'll start off with AZX, that's my parent isotope. That would decay into A, Z plus 1Y. So again, the key thing is with beta negative decay, you have a neutron turning into a proton. So if a neutron turns into a proton, your number of nucleons is not changing. But if your neutron changes into a proton, your atomic number would go up by 1. We emit an electron, and you emit an antineutrino. Okay, so the second mysterious particle that physicists were missing was the antineutrino. That's going to carry away the remaining kinetic energy. We also have beta plus or beta minus decay. Or sorry, beta plus or beta positive decay. Now, this one involves a transformation from a proton to a neutron and produces another subatomic particle called a positron. What's a positron? It's a positive electron. So a positive electron would have a mass of 9.11 times 10 to the negative 31 kilograms, but its charge would actually be positive 1.60 times 10 to the negative 19 coulombs. So proton turns to a neutron, you also have a positron, and you get a neutrino. So if you look at our nuclear equation for this, we would have AZX, that's my parent isotope, would give you, okay, proton to a neutron is not going to change the nucleon number, so we still are left with A. But if I go from a proton to a neutron, then I then have one less charge. Okay, so then I would have Z minus 1 for my charge on my daughter isotope. You emit a positron, 0 plus 1 beta, and your neutrino. And just to point out here, a positron is a particle with the same mass as an electron, but with the opposite charge. Now, here's a little way this is what I used to memorize, like what kind of particles emitted in each of these things. Okay, so when I see beta negative decay, here's what I'm thinking. Beta negative decay, what kind of an electron am I getting? I'm getting the negative one. Okay, so that's just the regular old electron, the negatively charged electron. Okay, electron has a negative charge. What kind of neutrino am I getting? I'm getting the antineutrino. I would associate the antineutrino as being like the opposite of the regular one. So maybe the regular one, like a regular something I might associate with being positive, as where the opposite is negative. So the opposite, or the antineutrino, is associated with the beta negative decay. Now, beta positive decay, what kind of an electron do you get? Well, you get the positive one. Okay, so that's a positron. Positron has a positive charge. What kind of neutrino is accompanied with it? The regular one. So think of positive as like the regular one, negative as in the opposite one. So positive regular neutrino is just the neutrino. And then the conversion from the parent isotope to the daughter isotope is just a matter of making sure that conservation of nucleons and charge is upheld. I'll do some examples of these different decay processes at the very end here. But first, we're just going to quickly talk about gamma radiation. It turns out that, so we talked in great detail in the last unit about how electrons have all these different excitation states, or these different stationary states. And it turns out that nuclei also have a series of excitation states. I'm not going to worry so much about that diagram. When a nucleus is in an excited state, the nucleons are further apart. When they're further apart, there is a greater amount of energy required to hold the thing together. Now, this might seem to be a bit of a contradiction, because you're like, well, wait a second. If the nucleons are closer together, wouldn't the repulsive force be trying to like really drive them apart? And wouldn't you need greater binding energy? Well, again, we're going to have to talk about another fundamental force, being the strong nuclear force. The strong nuclear force actually operates better when the nucleons are closer together. And when they're further apart, it does not. So if the nucleons are further apart, this other strong nuclear force has more difficulty doing its job. So you'd actually require greater binding energy if the nucleons are further apart. Now, just like with electrons don't like to be in the excitation state. They want to go back down to the ground state where they are unexcited. So they're going to try to go there. Same with the nucleons. If they're further apart in an excited state, they're going to try to go back down to a state where there's less binding energy. So when a nucleus undergoes alpha or beta decay, oftentimes the daughter nucleus is left in a highly excited state. And then, which the highly excited state means the nucleons are far apart, and then they want to move to a state where the nucleons are closer together. As the nucleons kind of rearrange themselves and move to a more optimal configuration in the ground state, they're going to emit a gamma ray photon. Okay, I'll make up like a really fake easy example. So let's say that we have like a nucleus that is consists of 1, 2, 3, 4 protons. Okay, so right now they're in an excited energy state where the protons are far apart. We're not going to worry about the neutrons here. Okay, the unexcited state would involve these guys coming a little bit closer together. Closer together, where that strong nuclear force can do its job better. And again, we'll talk about the strong nuclear force later. So in a bit of a closer configuration. Now, when these guys move, so I'll just focus on the movement of one of these particles. So let's say that we're looking at this proton. Okay, so this guy right here. When this proton moves from here to there, okay, it is going to accelerate. What happens when you have an accelerating charge? It emits electromagnetic radiation, according to Maxwell's principle. So this is where we get gamma ray photons from. Gamma ray photons are produced typically as a result of radioactive decay, where our daughter isotope is in an excited state, and in the process where the protons move to an unexcited state and get closer together, they accelerate and they emit a gamma ray photon. They need less binding energy to be here because, again, of that strong nuclear force, to be discussed later. Okay, I'm just going to erase this, and let's look at just one example. Okay, so this would be the beta negative decay of boron 12. So in the beta negative decay of boron 12, your parent isotope, boron 12, would turn into carbon 12, and you would also emit an electron and an antineutrino. This little asterisk attached to the carbon is telling me that the carbon 12 is excited. So we've made this conversion, but the nucleons are not in an optical configuration. So what they want to do is they want to move to an optimal configuration. When they move to an optimal configuration, so you go from 12,6C this is the excited state, and we go to 12,6C, this is the unexcited state. Your protons accelerate, and when they accelerate, we emit a gamma ray photon. Okay, so this is usually accompanied with any radioactive process. Okay, so let's do a few examples here. So we're going to write complete nuclear equations for alpha decay of radium-226, beta negative decay of actinium-230, and the beta positive decay of neptunium-234. Okay, so let me grab my periodic table here. Okay, so let's do alpha decay of radium-226. So radium has an element symbol of Ra, I believe. So we have Ra. And radium is, I'm going to try to locate it here. Okay, which atomic number is radium? Why can't, oh, here it is. Okay. Radium has an atomic number that is 88. So it's got 88 protons to it. 88. And it tells me the nucleon number, which is 226. Okay, it's going to spontaneously decay. Again, this nucleus is unstable just because there's so many protons in it. So it's going to undergo alpha decay. Alpha decay involves the emission of an alpha particle, which is 4,2He. And you're going to get some kind of daughter nucleus. So it's up to us to figure out what the daughter nucleus is. Okay, so what's going to be the charge number on the daughter nucleus? Well, whatever the charge is on the daughter nucleus, it has to add up with the 2 to give you 88, which means in order for conservation of charge to work, this number has to be 86, because 86 plus 2 would be 88. How about the nucleon number? What plus 4 would be 226? Will it be 222? Okay, which element in the periodic table has an atomic number of 86? That should be radon. So radon is Rn. Now, even though this radon is most likely to be in an excited state, we don't need to show the breakdown of the excited state to the unexcited state of the gamma ray unless we're specifically told to do it. Okay, so we can kind of just stop there. Okay, how about beta negative decay of actinium-230? Okay, so actinium-230 would have a nucleon number of 230, and actinium is 89. Atomic number 89, 89 protons, and it has an element symbol that is AC. Okay, so it undergoes the beta negative decay. Okay, so what are the two subatomic particles involved in beta negative decay? Okay, what kind of an electron? The negative one. Okay, so the negative electron would be 0, -1, beta, or you can write down the symbol E. What kind of a neutrino is involved in it? Well, what does the negative mean? The regular neutrino or the opposite of regular? Well, the opposite of regular, which would be the antineutrino. We put a little bar on top to indicate the antineutrino in comparison to the regular one. And then the daughter isotope, well, now it's going to use conservation of nucleons and charge to get it. Okay, so what plus -1 would be 89? It'd be 90. 90 plus -1 is 89. The nucleon number doesn't change because we're just having the conversion from what's going on here. If we're going from 89 to 90, we're turning a neutron into a proton. So neutron to a proton does not affect my nucleon number, so I just stay at 230. Which element has an atomic number of 90 on the periodic table? That is thorium, so TH. Okay, and the final one, the beta plus decay or beta positive decay of neptunium-234. So nucleon number 234. Neptunium has an atomic number of 93. Okay, this is going to spontaneously decay. Okay, so what does the positive tell me? Okay, what kind of electron are we talking about here? The positron. The positron has a nucleon number of 0 because it has no neutrons or protons, but it has a charge of +1. And we can use the symbol beta to represent it. What kind of a neutrino is involved with this? The plus means the regular neutrino. So the regular neutrino, I just used the regular V symbol for it. And then it's just a matter of conservation of nucleons and charge to get the daughter isotope. Okay, what +1 is 93? 92. What +0 is 234? Well, just 234. Again, all that's happening here is if I'm going from 93 to 92, it means I'm losing a proton. So in beta positive decay, we're going a proton to a neutron, and that keeps my number of nucleons constant. And which element has an atomic number of 92? I feel like I want to say uranium, and it is uranium. Okay, so those are my complete equations. And again, just be aware that technically speaking, like usually the daughter isotope would be excited. So if it was excited, it'd be like 234, 92, and you put a little asterisk beside it. And then that would break down into 234. So the nucleons move around, 92, the U plus the gamma ray, 0, 0, gamma. But again, we don't need to show that, okay? We would only ever show this part here if we're identified to also show the emission of the gamma ray. But if not, then we would just simply focus on the equations I've shown up here. We don't need to worry about the transition from the excited to the unexcited state. Okay, so you complete an assignment that's called the radioactivity hand-in assignment. Most of the assignment is just playing around with the equations, like in example 1. There's a few conservation of mass energy calculations, but a big part of the assignment involves reading a couple of pages that I scanned from the textbook that talk about the biological hazards of, let's go back to the first slide here. Just kind of like look at our learning outcomes. Yeah, so I did talk about alpha, beta, and gamma radiation in terms of their nature and properties, but I did not talk about the biological effects. So the point of the article is you read about the biological effects of all these different types of radiation. And again, just regarding the gamma emission, if you look at the learning outcome 2 here, it just talks about doing alpha and beta negative, beta positive decay. But we don't need to also show that additional step where we're going from excited to unexcited. Okay, so that's it for this lesson. And in the next one, we'll talk about how long does it take for the radioactive decay to occur. So we'll get into some half-life calculations then. And I will talk to you in that lesson.